All right, I know you guys are thinking, Mr. Collins out here today, free day. Not quite. You actually have something very important to do today that we will discuss more in detail next Tuesday, but you're going to have a good base if you're going to survive next Tuesday at all. So here's the deal. You have these new definitions that you need to get down. If you need to go ahead and pause the video now, you can. But also know that I'm going to have them on the next page, which I'll go through more in detail, just like a legitimate opener, as boring as they've been so far. So we have some more things for your toolbox, some more for your flashcard deck, if you would. So let's talk about these definitions and maybe try to get a pictorial representation of what these mean, because in the end, you're going to have to be able to recognize these by sight. So check it out. If C is a midpoint of AB of course is a segment. That's the notation we're using. And then AC is congruent to AB. So it's really an if-then statement. So check it out. So if I have this segment AB, and then somewhere in the middle, and precise middle this time because C is what we call the midpoint. So C is in the middle. I can conclude actually a couple things. The picture thing I can conclude is that I can add some hash marks to my segments, indicating those segments are now congruent. I can also write them out as AC congruent to CB. Okay? And that's all it's really saying is that if C is in the middle, then it cuts that segment into two congruent parts. And you're going to see a lot of these follow the seam intersection today. So that's midpoint. Let's talk about bisector. So if AB is a bisector of CD, and those are both segments, and notice how this language is kind of arranged, and it's an important thing to note right now. AB is a bisector of CD, which means AB is actually cutting CD. So CD is the cuttee, AB is a cutter. And although it does have to pass through the central point E, it doesn't have to do so at a 90-degree angle. It just has to cut it in half. So we have AB, which cuts CD in half. That's what it means to bisect. Bi means two, sect means cut. And so what this authorizes us to do is to, one, on a drawing end of things, okay, on the drawing end of things, it allows us to actually mark those as being cut into two congruent parts. On the notation end of things, it allows us to write a statement, CE congruent to ED. And I believe I actually have that wrong here. Yeah, so let's go ahead and scratch that guy out. That should actually be CE congruent to ED. And I apologize for that. I didn't quite catch that from before. Okay? So just like definition of midpoint, all this is really saying is that if I have this thing that goes through the middle, whether it be a point or whether it be a line, I'm basically cutting my line to two congruent parts. The importance of this is twofold. One, I now have a name to call this phenomenon, bisector or midpoint, but also it takes this picture, and I'm going to go ahead and highlight this and say like yellow, it takes this picture and transfers it into a workable statement. It's not quite an equation, but it will be eventually because of the definition of congruence. But again, we have this conversion from a picture to a statement. And that's what's really important about these. It allows us to take something that we see into something we can actually work with mathematically. Right? So there is a second part to the idea of bisector, and that's having to do with angles. We have this angle CAD, and of course A is going to be the vertex of this angle. Here's C, and here's a D. And then we're going to introduce this new line segment, in this case AB. A, of course, is shared. B has got to be somewhere in the middle. So if this is indeed the case, if I have this AB which bisects, it cuts angle CAD, and then we actually get two results. One is a pictorial result. Here's A and here's D. B is in the middle. So the pictorial result is that these angles are now going to be congruent, of course showing that by using the single tick mark. And of course the written out result is that angle CAB is now congruent to angle BAD. Now this isn't mind-blowing. This is just going to be a angle version of what bisectors were for segments. In the most simplistic, non-object permanence kind of way, what this basically says, if I cut an angle in half, then each of those parts should be the same. That's all it says. That's all this one says too. If I cut a segment in half with a line, each of those two partial segments are now congruent as well. And of course, whoa, back up there. And then of course, if I cut a line in half with a point, then those two parts are congruent. Again, not super mind-blowing, just something to keep in mind. Now here's two that kind of go together. And here's where you're going to have to be really, really careful. So check this out. If AB is perpendicular, and that's what that sign means, perpendicular to CD at point E. So let's draw some things. So we have AB segment. We have CD segment. Okay, and they're going to intersect perpendicularly at E. Okay. That implies that those angles are right. In fact, they're all right. I mean, of course they're all right. Yuck, yuck, yuck. Okay, so these angles are right. In fact, they're all right. All four of them are going to be at the same time. So notice perpendicularity tells us right angles, and that's all it really tells us. You guys are going to forget about that later, but it's going to become really, really important. Okay, so CEA and angle DEB, and actually all of them are going to be right. Okay. Notice it doesn't tell you a number. It just tells you that they're right angles. If you want to convert that to a number, you're going to have to reference the definition of right angles. So again, you're kind of seeing a chain. If these lines are perpendicular, the angles are right. If the angles are right, then their measurements are equal to 90 degrees. We're seeing a chain, a chaining together of statements, a chaining together if then statements even. So that's what we got going on. Now the last piece is probably the most confusing one, and it's because I actually hate this statement. I hate it. It is the worst statement in the world, but I would be completely unjust as a teacher if I didn't show you CPCTC. Now what CPCTC stands for is corresponding parts of congruent triangles are congruent. Now there is another name for this, and that is simply the definition of congruent triangles. It means the same thing. So here's all it's really saying. If I have this triangle over here, let's call it ABC, and I have this other triangle over here, let's call it DEF, and I know these triangles are congruent in the way that triangle ABC is congruent to triangle DEF. What is all this is saying is that if I know this is true, then this side is congruent to this side because they're corresponding. And BC is congruent to EF because they're corresponding, and AC is congruent to DF because they're corresponding. And if that wasn't mind-blowing enough, this angle at A is congruent to the angle at D, the angle at B is congruent to the angle at E, and the angle at F is congruent to the angle at C. This is all it means. If I know two triangles are congruent, then all their parts are congruent too. Period. That's all it is. Now, I don't like using CPCTC because it reduces it down just to like this crazy little acronym. What I rather really have you kind of visualize and absorb that congruent triangles should have every possible measurement also congruent. That's what I'd like you to know. CPCTC, however, is going to show up two places where you should know what it means. Number one is going to be on your ACT test or SAT test when you eventually take it. They use CPCTC, which is why I'm showing you that now. The second place is going to be on future um, standardized tests you'll take in this class even. So even though I don't like it, I acknowledge the need to use it because that's just how test makers talk about CPCTC. So again, don't freak out. It's just one of those things where we have to show you, even though Mr. Collins personally doesn't like it. So an example of how this might be used would be kind of like this. So let's say I had these two triangles. Okay? And let's say I know that triangle JLF is congruent to triangle MRC. Okay, and then I have to say prove angle 1 is congruent to angle 2. Well, this is automatic, and here's the reason why. Angle 1 and angle 2 are congruent because of CPCTC, because these two triangles are automatically congruent, therefore the angles have to be as well. So CPCTC is just a definition of congruent triangles, but hey, they want to give it a fancy name, so I say let them give it a fancy name. Okay, so the next thing I need you guys to do is roll up the video for our first kind of proof, which I'm going to reveal may be a nice, easy way to write a proof.